Hi everyone. We're going to talk about rational exponents, but in anticipation of that, we're going to do a warm-up on number patterns. So here we have a sequence of 3 numbers, and you are asked to find the next 2 terms in the sequence, and then you need to describe the pattern in your own words. So go ahead and do number 1 and 2, and then when you're done, you can continue the video. Okay, so hopefully you got that the next term here is -8 and then -14, and you can either write down that you add -6 each time, or you could subtract 6 each time. And because you are adding a positive or a negative number each time, this is actually called an arithmetic sequence. We're going to see this in a later chapter, but just for your reference, for your information, this is called an arithmetic. All right, number 2 is not an arithmetic sequence because you are not adding the same number each time, but this one you can see you add 2, and then add 3, and then add 4, and then add 5. So the next one would be to add 6, which would make 27, and add 7, which would make the next term 28. So you're going to add numbers that increase by 1 each time. Or you can see that when you go to the next step, you can see there is a difference of 1. And if you looked at that in a table of values where you had the term, just the term number, and then this number here, oops, 1. Oh, I want to do that. No. There we go. Yeah, I wanted this one here. Okay. Oh my goodness. Okay. I don't know what's going on here. Anyway, the second finite difference is 1. Okay. Now, take a moment and do number 3, and go ahead and do number 4, 5, and 6, and we will check that after you stop the video. So 3 through 6. Okay, so for number 3, let's see here. This one is a tricky one. You're not adding the same number. The numbers that you're adding here, this is +2, +1, +3, +4, +7. These numbers don't seem to follow any particular pattern. However, if you take a look at these numbers, they mimic the numbers above here. Okay, so you see 1, 3, 4, 7, 1, 3, 4, 7. So what you can do is, there's a couple different ways of thinking about this. Let's go back to pen. So for the number 3, to get to number 4, you had to add 1 to the previous number. And to get to the number 7, you had to add 3. To get to number 11, you had to add 4 to 7. And to get to the number 18, you had to add 7 to 11. So it looks like the number 7 comes from this 7. The number 4 comes from this 4. The 3 comes from the number before that. So if we want to articulate that, what we can do is say, add the 2 previous numbers or terms to get the next term. So what would that make us? What would be the next term? Well, 11 plus 18 is 29, and 18 plus 9 is 47. Okay, and this is very similar to a Fibonacci sequence, but the first two numbers of a Fibonacci sequence begin with 1 and 1, and then you add the two previous numbers to get the next one. This is a really famous sequence of numbers, and you see this pattern in nature, and this one is called the Fibonacci sequence. This one right here. Okay. So this one is a Fibonacci-like sequence. Okay, let's go to the next one. And oops, here we are. Oops, no, we want to be here. Okay, so here you can see that it's not adding. If you look at it closely, the 3, 9, 27, 81, they all have a common factor of 3. So you're actually multiplying by 3 each time. This is a multiplying. So 81 times 3 is 243, and 243 times 3 is 729. So you're going to multiply the previous term, multiply by 3 to get the next term. And when you multiply by the same number, this is called a geometric sequence. So please write that down. This is called a geometric sequence. Okay, here for number 5, you're multiplying by the same number, in this case 3, but the signs are changing, so you're just multiplying by a negative 3 each time, and so on and so forth. So 108 times negative 3 is 324, negative 324, and negative 324 times 3 would be 972, because a negative times a negative is a positive. So again, here we're multiplying by negative 4. And this is also a geometric sequence, because we're multiplying by the same number each time. And the last one is actually also a geometric sequence, but you're multiplying by a number less than 1. In this case, you're multiplying by 1/2 each time. Okay, so this would make it 1/32 and 1/64. And you're multiplying by 1/2. Or you can say divide by the reciprocal or the multiplicative inverse, which is 2. All right, let's go to the next page. And these are a little bit more challenging. Go ahead and just take a look at them, think about it, and just try your best and submit your responses. Okay, so after thinking about it, these are the 1 square root of 2, 2 square root of 2, 4 square root of 2. So the next one would actually be 8, and then 8 square root of 2. Now, why is this? Well, in order to get from 1 to square root of 2, you just multiply by square root of 2. And if you take square root of 2, let's do this. Okay, I'm going to take 1 times square root of 2 equals square root of 2, and that's how I get this one. Now I'm going to take this one, square root of 2, multiply by the factor square root of 2, and I get 2, which is this one here. I'm going to just continue in this fashion, multiplying by the square root of 2 each time, and you can see that it actually works out to be the next number in the sequence. So this is also a geometric sequence, but in this case, our the factor that we're multiplying by each time is, the common factor is square root of 2. So to get 8, we have 4 square root of 2 times the square root of 2. We know square root of 2 times square root of 2 is 2, and 4 times 2 is 8. So how do we describe the pattern? We're multiplying by the square root of 2 each time. And again, this is a geometric sequence. Okay, for the last one, oh, I'm sorry, not the last one, second to last one, instead of multiplying by square root of 2, we're actually multiplying by square root of 3. Okay, so let's go ahead and take a look at 9 square root of 3. And we multiply by that by the square root of 3. We get 9 times 3, which is 27. And then 27 times the square root of 3 is simply 27 square root of 3. Okay, and then the last one. This is called the cube root of 5. Why is it the cube root of 5? Because if we take cube root of 5 times the cube root of 5 times the cube root of 5, we get 5. An easier example would be the cube root of 8. What would be the cube root of 8? Well, the cube root of 8 is 2 because 2 times 2 times 2 equals 8. So the cube root of a number is what number times itself times itself. In other words, what number times itself 3 times is equal to the number that's inside the radical symbol. Okay? So in this case, we have 1. What are we multiplying to get cube root of 5? Well, seems like we just multiply by the cube root of 5 to get the cube root of 5. That gets us to this term. What about if I multiply, this is a cube, 3. What about if I multiply the cube root of 5 by the cube root of 5? Hopefully you remember that when you're multiplying radicals, okay, and you take the numbers inside the radical sign, and then you multiply them out, and this is either the cube root of 25, or you can just keep that as the cube root of 5 square, okay, which is this one. And then the next one would be cube root of 5 square times the cube root of 5. Well, that would be the cube root of 5 times 5 times 5, and by definition, that is equal to 5, okay? So let's go and skip to 25 here. So we know we're just multiplying by the cube root of 5, okay? Oops. We're going to take 25, multiply by the cube root of 5, and we get 25 cube root of 5, which is what goes right here. And then the last one would be 25 cube root of 5 times the cube root of 5. And that can be written as either the cube root, 25 cube root of 25, or 25 cube root of 5 square. Okay, so I'll just go ahead and write 25 cube root of 25. What's the pattern? We're multiplying by the cube root of 5. And therefore, since we're multiplying by the same number each time, this is a geometric sequence. Okay, so for the last 1, 2, 3, 4, 5, 6, the last 6 were all geometric sequences because for each of them, each sequence, they had a common factor. You multiply by the same number each time. All right, so that was a warm-up, and so the next video is going to be on rational exponents, and you'll see why we did this warm-up, because I wanted you to start thinking about radicals. Okay, thanks. Bye.